Hello again. This is Quasi-Experimental Design Data Analysis, Part 2, with the post-test only two-group design. And we're going back into the PowerPoint just for a minute, and then we'll be all in the data, I believe. So here we go. This is where we left off after doing the power analysis. You may remember the researcher wanted to know if a brief two-class period intervention in hands-on inquiry-based real-world math problem solving would lead to higher math skill or math interest outcomes at post-test compared between a group that received the treatment and a group that did not, where there was no random assignment. So the big issue when there is no random assignment is, does selection or the way people get into the groups make a difference? Is there any difference at post-test that's attributable to pre-existing differences between the non-randomly assigned groups, or also what they call the history effect, anything that happened to one group versus another other than the treatment? So for instance, were the people who were in the class that the instructors didn't want to give up instructional time, were they all more advanced students? Just maybe it had to do with the class sections they were in. Maybe they were what they call sometimes the daytime cohort. So they were getting a very intensive exposure to their education, and they had lots of time to do homework and things like that. The other people were something like, I'm spacing out the name for those people, but the ones who are teaching full-time while they're going to graduate school, which is a very intense experience on its own, and they may not have a chance to do homework. So is there a difference that's attributable to pre-existing differences that have to do with the way people got into the different groups, or also perhaps something that happened to them? So perhaps the instructor that didn't want to give up instructional time, those instructors were the ones that were teaching more intense instruction, or they were teaching something during those class periods that was profoundly different. So, you know, once you've got your groups, there's nothing you can do to make them the same, particularly if you don't have any control over the instructor who's in the comparer instructors, whatever the instructors, whatever's happening in the comparison group. So you can't post hoc randomize people. What the only thing really you can do, and you'll see this in papers, is you can compare the two groups post hoc to see with descriptive, essentially descriptive, but also we'll be looking at inferential statistics to see how different they were to start with. And that is what we're going to do. The things that you can do is, if you have any known pieces of background about these people, if you have continuous variables that are descriptive of them, then you can compare the two groups on those descriptive variables. They're independent groups, so you can use independent sample t-tests. And the question to ask yourself is, in this case, these are at pre-intervention. We have no pre-test, but these are existing known information about what happens, what has already happened to these people before one of them gets the treatment. And so what is the outcome you want to a t-test before treatment? And just think about that one. And the other question is, if you have categorical variables, like you've got a variable for gender, male or female, what you can use the chi-squared test, and what do you want the outcome of that to be? Do you want or not want there to be differences in the gender makeup of the two groups before the treatment. So the assumption is, hint, hint, that if they were randomly assigned, there would be no differences. So the question is, are there differences, and what outcome are you looking for? So that's all of those slides. We are going to switch shares and go into the data and actually see how these questions about the possible selection bias, that's really what you're looking for, is whether or not there's systematic differences between the groups when you assign them, given that you're not randomly assigning them. And also, we'll just run the test for the outcome. So one thing you were going to want to do is you're going to want to find out, did he meet his expectation for power? And remember, he wanted 73 in each group. I'll just actually run through the variables on this really quickly. I'm sorry I didn't do that. You have this just assigned ID for each person. You have gender, male and female. It's just reported that way. I think there's some people who didn't answer it. You have a continuous variable that is a scale variable. Gender was nominal. You have a general math test that is a test they took in their freshman year. You have the highest level of education they'd attained. People with high school degrees and associate degrees, those would be your undergraduates. People with BAs, MAs, and MA plus 30s, those would be your graduate students. You have whether they went into the comparison group or the treatment group. So the comparison group people took the post-test, but they were in a class that did not have any experimenter control over manipulation. And the coded 1 if they were in the group that received the 2 class-long hands-on inquiry material. And then you have the 2 post-tests on interest and math skill. So first thing we want to do is we just probably want to describe the sample, see how many people we have. I'm going to look at the frequency actually just in terms of the groups to see how many people we got into the sample. So just going to look at the frequencies that people got into the sample. We'll do the rest of that later. There are 160 people in the sample. His target was 146. So he just barely exceeded that. And the sample is actually balanced with 80 people in each group. And that's what we call a balanced test. T-tests prefer, people doing T-tests prefer a balanced sample, and he just happened to get it. I don't know why I say he's a he, but that's what I started off saying. I hope, actually, I believe you cannot see that outcome. I have to switch the outcome screen, sorry. So this is the result of the frequencies table. 80 per group, 160 total. So going back to the data. So what we said we would do is look at variables that had been collected prior to or that occurred prior to the treatment group getting the intervention. So those would be our gender variable, age, general math skill, freshman year, and level of higher education. I love the way this doesn't work very well, the annotation. I'm learning. And so let's look at general math first. That's a continuous or scale variable. And so we're going to compare the general math background that these students had as it was measured in freshman year long before they received the treatment. And so that's going to be an independent samples t-test. And we might as well, just for the sake of efficiency, we've got their general mass, and the other continuous variable that we know about them prior to treatment is their age. So we'll do them both in the same run. That's called a run, is if you run the program in one go rather than in two. And the grouping variable, because we're going to be comparing these two groups, the quasi-experimental conditions, comparison or treatment, goes here. And we have to define the groups. So one group is our treatment and one group is our outcome. You have to check if it's different data about how these things were coded. So I happen to know that, I'm sharing this. Yeah, it looks like I am. Oh no, I'm not. Wow. I'm sorry. Every time I bring up new windows, I have to bring up a new share. Okay, so going backwards, I want to redo this because you didn't see it. So we are going to test between group differences prior to intervention on general mass and age with between the two groups on the quasi condition. And we have to define what are the two groups in the quasi condition, and one is group 1, one is group 2. Those are how they've been coded. You have to be sure that the numbers that you define match the numbers they were coded. And there's no particular interesting thing under options, so I'm just going to run this. And then I have to bring up that screen for you so we see the output. And the question I asked you is, what do you want the output to be? So one thing you want to look at is, first of all, your ends. You have one person, you have two people, oddly, one in each group. Very balanced design, who left out the age question. So you only have 79 people in that group. That's not, or actually, I'm sorry, 144 people in that group. That's not a problem. And those are the descriptive statistics for each group. And we want to see the results of the test. So always with a t-test, the first thing you look at is the significance level for Levene's test for equality of variances, because equality of variances or homogeneity of variances is an assumption. And I hope you remember that with tests of assumptions, you do not want significance. It is the null hypothesis that the variances are not different, and you want to retain that hypothesis of no difference between the variances. You want the group to be the same if it's an assumption. And so our significance level for both on Levene's is about 0.05. So we have not violated that assumption. And then for the t-test of equality of the means, you have no significant differences in the means. So what this tells you, do you want significant difference between the means at pretest? No. You want the groups to be similarly distributed, similar means on age and general mass before you do anything to them. That means that they're more similar. It means that if there's something different about them at outcome, you're slightly better to attribute it to your treatment. Now, you know that their age and their general math skill is similar one of your target variables is interest, which you haven't measured before the intervention. So they could be different on interest, but you're doing the best you can with these data. And this is not unusual. You see it in the literature all the time. There are a lot of kind of issues with it. But sometimes sometimes it's what your data supports. And I have no problem with that personally, as long as you understand what the limitations of the tactic are. And the limitations are that first and foremost, that you only know that the groups, you only have any evidence that the groups are similar on the things that you can compare them on, where you have data. And in this case, we have age, we have general math skill at freshman year, and we also have a couple of categorical variables, which we will get to now. So the chi-square is found, I think, in a couple of places in SPSS, but I always get it through crosstabs. And our, we're gonna put quasi-condition in rows. So we're gonna see one row on top that's the treatment condition and one row underneath that's the comparison condition. And then you'll see the categories of the categorical independent variables arrayed as columns. Oh, I just did that opposite. Okay, let me go and do it right. And let me see if you can see this. No, sorry. Sorry once again. So descriptive statistics, crosstabs, here's the crosstabs window. Let me confirm that you're seeing it. So we are going to look at quasi-condition in rows, and our categorical variables are gender and their highest level of education. And under statistics, we want to ask for chi-square statistics. And I believe you've covered chi-square, I hope so. Chi-square tells you whether there's a systematic relationship between two categorical variables. So in this case, using highest level of degree, is there a systematic relationship between what group they get into and how much education they have? And ask yourself, do you want there to be prior to the treatment being administered? And we only have 159. Share the new thing, the output. We have 159 people showing up in the gender by quasi-condition category, because we have one person who didn't answer gender. We have all 160 people answered the question about higher education. And in terms of the distribution of quasi-condition over the categories male and female, you see that there are a lot in both conditions. There are much more females than males. That's to be expected in education. But according to the chi-square statistic, which is 0.522, it isn't systematic. In other words, it's a similar pattern for both the comparison and the treatment group. There's no systematic difference between the distributions of males and females in the comparison versus the treatment group. And that is what you want. Typically, when you're looking to compare samples prior to an intervention, you want evidence that they're the same. So you want no difference. You do not want to reject the null hypothesis. And looking at their highest level of education, you find these are your undergraduates, and these are your graduate students just coming fresh out of graduate school. These are people with 1 master's degree or a master's plus 30 already. And there's nobody with a PhD. And there's no significant difference in the distribution of highest prior degree when among the students who are going into these conditions. So this is all good. This means that as far as you know, the two groups are pretty similar. they're of similar age, they're of similar mathematical skill prior, quite a bit prior, at freshman year. They're similar in their age distribution, and they're similar in the distribution of the amount of education they've had. They're similar. But you don't know about anything else that hasn't been measured that might make them systematically different. That is the key difference between random assignment and non-random assignment, is that the assumption with random assignment is that two groups are pretty much the same on everything, whether it's been measured, whether it's not measured. As whole people with all their attributes, they are probabilistically the same. And therefore, it's only the stuff that happens to them after assignment that probabilistically makes them different afterwards. And that's just a huge advantage, because if you can say the only real thing that happens to them afterwards is they get this treatment, then probabilistically they were all the same before, within, the bounds of chance. And if they're different afterwards, and that's the only thing that happened, then you have an argument for causation. If the only things you know is that they were kind of the same on gender, and they were kind of the same on age, and they were kind of the same on these other couple of things, but there's a whole world of differences that you don't know about, and you can't assume that they were different because they were just chosen by chance, is a much less strong argument. So, but it's the argument we can make. They were similar on these things that we know about them before they got into the condition. Then 80 of them received this treatment with the inquiry, and 80 of them just got business as usual according to whatever their instructors gave them. And so we are going to go back to the data, and don't really have to do that, but we will anyway. And we want to see what the two distributions look like at post-test. So we have a couple of minutes on this. I'm going to call up a descriptive on this under Explore. And this is the Explore menu. And I just want to look at the post-test scores organized by quasi-condition, which is my independent variable. So these are my dependent variables that that I measure after the intervention. This is the way I want to divide the way I look. I want to look at them according to the condition of the independent variable they are in. That's called a factor here. Sometimes people call it a factor. And the only thing I want to look at is the box plot. So I am going to draw up the box plots, tell it okay, switch my share, output, and there's the box plot for, can't see as much as you can. Oh, for interest. So you see that the treatment group has this is the box is representing the interquartile range. This is the maximum score. This is the minimum score, and this is the median. Line is the median, interquartile range, maximum. Actually, this isn't the maximum. This is, I don't know, I think it's probably then, remember. Oh, this is the 95th percentile, I think, because they show outliers with stars. People, sometimes there's something called the 5-number summary that, it's the 5-number summary that uses, this represents the 5-number summary. The min and the max is more common on a box plot, but SPSS does it like this. So anyway, they tell you basically the same thing, is the spread of the distributions and also the differences between their central tendencies. And the direction of the differences between. So treatment looks like it's got a higher range considerably than interest. And then we can look down here on skill, and there does not seem to be a considerable difference. There's a wider range, it looks like, for treatment than for comparison, but they are in the similar area of central tendency. So that's just descriptive. It doesn't draw any conclusions, but we kind of know what it looks like. And now I'm going to go to the actual test, just under compare means. And we're asking for an independent samples t-test. I'm not sure that you can see that. Now you can see it. And we want to test the post-test differences after treatment, comparing the two groups in the quasi-experimental condition, group 1 treatment and group 0 comparison. And I don't think we have any issues that we need to look at with that. Oh, we already defined the groups. So bring up the output. And you can read the descriptive means. You may have gotten them elsewhere. Just like you saw in the box plot, the mean for the treatment group is higher than the mean for the comparison group on interest, and it's just slightly lower than the mean for the comparison group on skill. Looking at the test, the first thing that you look for is the Levene's test for equality of variances, which you want to be above the 0.05 significance level. Now, for interest, the variances are not the same. They're statistically significant difference between the variances. So differences in the variances is probably not due to chance. So first of all, let's go back and look at that. And the main area, okay, so the width of the interquartile range is similar, but you see that the full range is much broader. You've got a much narrower range between the two whiskers. And so you have more kind of outlying values. So that's where that's coming from. Now, what do you do about it? Well, it just so happens that there's an easy fix for that in that's offered as a default. I mean, it's not really, this is a question about how severe the problem is, partly. The t-test is said to be robust to departures from the assumption of homogeneity of variances, particularly when you have equally sized groups. So, and you happen to have an altered test as a default. So that's a pretty handy workaround. You would report that, and you notice that the T results are identical. The significance level is very low for both tests, and the degrees of freedom is what gets adjusted and by the Levene's test. So one of the things my students always ask me is, how do I report that? And what you report is that the assumption of equality of variances or homogeneity of variances was not upheld. Actually, you don't even need to report the F statistic. Just say it was not upheld, and so the Welch's test, this is called the Welch's test, was used instead, or is reported instead. And so Welch's T equals 14.51 degrees of freedom, parentheses, underneath or beside the T, 152, you can round that. And in terms of reporting the significance, you never report P equals 0. everything has some probability. So you can report P is less than 0.01. That's what I would do. And you can report an effect size if you want to. I'm not going to go into effect sizes or confidence intervals. I'm leaving that to John. But you do have a difference in interest after the intervention, and it is the treatment group who is more interested in that after the intervention. So that's cool. They take a hands-on inquiry experience, and at outcome, they're more interested. It's hard to attribute it to that because they may have been different on interest to start with, but they're not different on anything else you know about. We're kind of saying that they're typical students in a school of education, in childhood education, in a mathematics course. We know of no reason they would be different, and yet they are different on interest after the intervention. They, on the other hand, are not different on their math skill. Does that mean that the math thing didn't change their skills, but it changed their interest? It's evidence in that direction. That's what it is. And I would say, you know, it's not the greatest evidence, but it's evidence in that direction. And I wouldn't throw it out. So that's basically it. What I hope I have covered in the section of the slides that go before is the, I don't know where I am. Oh, I stopped sharing. That's what I did. That's what I failed to do last time. So what I hope I've covered in the first part of this two-part screencast is the overall layout of this quasi-experimental design on math interest and skill using hands-on inquiry, and the power analysis for determining the sample size, and the general concepts of what you might look for to determine whether you had balanced groups when you did not have random assignment. And then in this section of the screencast, we went into the using independent sample t-tests and chi-square to see whether post hoc your two groups in the absence of random assignment were similar. And in this case, you failed to reject the null hypothesis that was that they were similar. So you found no differences between the two groups prior. And so you were going to go ahead and consider that they were, to all known extent, similar groups, and yet when one had this treatment, their interest significantly increased. And probably you would find a pretty large increase in that interest. So a large effect size if you wanted, and you certainly can if you want to. You're going to get the data. And if you wanted to check any of those things, please, I hope you will. Have a good night or day wherever you are. Bye.